When you step out of the sweltering summer heat into an air-conditioned room, the immediate sensation is pure relief. The intuitive assumption is that the machine humming in the window or on the roof is actively producing that cold air, much like a traditional furnace produces heat. Thermodynamics dictates a different reality. In physics, cold does not exist as an independent force or energy. It is strictly a negative state, the mathematical absence of thermal energy. You cannot manufacture an absence. Look at this cross-section of a conditioned space. The system is not injecting chill into the room. Instead, thermal particles, the heat itself, are actively extracted from the interior and physically pumped out into the hotter exterior. Heat naturally flows from a warmer area to a cooler one, forcing it to move in reverse. Pulling energy from a cool room and dumping it into a hot summer afternoon defies that natural gradient. It requires a specific mechanical architecture to force the heat to move outward. To understand modern refrigeration, we have to discard the idea of a machine that makes things cold. What we are actually looking at is a highly engineered, continuously operating heat pump. This architecture is called the vapor compression cycle. As this schematic shows, it relies on a continuous loop moving through 4 distinct mechanical nodes: the evaporator, the compressor, the condenser, and the expansion device. Flowing through this closed loop is the refrigerant. Think of this as the circulatory fluid of the system, a chemical compound tasked with physically carrying thermal energy from one node to the next. The system directs this thermal transfer by manipulating 3 specific variables of the refrigerant: its pressure, its temperature, and its physical phase, alternating between liquid and vapor. By controlling these variables, the architecture is divided into 2 distinct zones. The low-pressure side on the left is optimized to absorb heat from indoors, while the high-pressure side on the right is engineered to reject it outdoors. The movement of thermal energy is dictated by the state of the refrigerant. Mastering the manipulation of internal pressure is how engineers force that energy to follow a path it wouldn't naturally take. We begin the analysis at the first indoor node, the evaporator coil. As the refrigerant enters this coil, the gauges show its exact state. It arrives as a low-pressure, low-temperature mixture of both liquid and vapor. A fan forces the warm ambient air from the room directly over this icy metal coil. This is where the physical interaction occurs. Following the laws of thermodynamics, heat seeks equilibrium. The thermal energy inside the warm air immediately transfers into the colder metal, and consequently into the chilled refrigerant flowing inside. Because the refrigerant has an extremely low boiling point, absorbing this heat triggers a phase change. The liquid boils and flashes into a low-pressure vapor. The air blowing out the other side of the coil is now cold. It hasn't been injected with anything. Its thermal energy has simply been stripped away and trapped inside that vaporized refrigerant. The evaporator functions as a thermal sponge. Its single purpose is to load the room's heat payload into the chemical bloodstream of the system. Carrying that absorbed heat, the low-pressure vapor exits the indoor unit and travels outside to the compressor. There is a common misconception that the compressor is responsible for chilling the system. It does the opposite. The compressor performs a mechanical action. It takes a large volume of the incoming vapor and physically forces it into a smaller, confined space. By compacting the gas, the molecules are forced together. The pressure increases, and as a result, the temperature spikes. The refrigerant is now a high-pressure, superheated vapor. This gas is no longer cool. In fact, it is now significantly hotter than the summer air waiting outside the unit. This is the compressor's purpose. It elevates the refrigerant's temperature so that it can overpower the outdoor heat, ensuring that thermal energy flows outward rather than stalling. The superheated vapor is immediately pushed into the outdoor condenser coil. Here, the extreme internal temperature of the refrigerant is pitted against the outdoor air. Even on a hot day, the outside air is cooler than the superheated gas inside the coil. Because heat moves toward a cooler space, the thermal energy collected indoors is forced to radiate out through the metal fins and into the outdoor environment. As this heat bleeds away into the atmosphere, a second phase change occurs. The high-pressure vapor condenses back into a dense liquid. The refrigerant finishes its path through the condenser as a high-pressure, subcooled liquid. When you stand near an outdoor unit and feel a blast of hot air, You are physically feeling this exact heat rejection process at work. The condenser completes the delivery. It takes the unwanted heat and dumps it outside. Now, the high-pressure liquid travels back toward the indoor unit, approaching the final node in the loop, the expansion device. The expansion device is a mechanical bottleneck, functioning as a precision metering valve. The system forces the high-pressure liquid through this tiny opening, allowing it to expand into a much larger volume on the other side. Pushing the fluid across this boundary causes the pressure to drop instantaneously. A rapid loss of pressure forces a corresponding loss in temperature. The liquid chills in a fraction of a second. The fluid exits the expansion device, completely reset. It is once again a low-pressure, low-temperature liquid-vapor mixture, ready to enter the evaporator coil. The expansion device serves as the reset mechanism. By collapsing the pressure, it recreates the cold state required to absorb room heat once again. Stepping back from the individual components, we can view the entire vapor compression cycle operating as a synchronized loop. Absorption, compression, rejection, and expansion do not occur in isolated steps. They happen concurrently, maintaining a steady thermodynamic rhythm. The architecture relies on two boundaries. The compressor and expansion device act as dividing walls, keeping high-pressure and low-pressure zones separate. The refrigerant never leaves this closed loop. It is a permanent circulatory system, changing physical states to capture and release thermal energy. Pressure manipulation is the engine driving the entire process, dictating exactly how the thermal energy moves. This brings us back to the opening reality. An air conditioning unit does not generate cold. It relies on passive heat exchange points. The evaporator acts as the indoor doorway for heat to enter, and the condenser acts as the outdoor doorway for heat to exit. These doorways are operated by active mechanical engines. The compressor and the expansion device apply the pressure changes required to push the heat along its path. The vapor compression cycle provides the physical proof. Refrigeration is the engineered displacement of heat. Mastering this specific thermodynamic loop is what allows us to stabilize indoor environments, regardless of the temperature outside.